Hello everyone and welcome back to the channel. Imagine your brilliant new API is suddenly bombarded by a single runaway client or worse, a malicious attack. Your servers get overloaded, your database crashes, and your entire application grinds to a halt. How do platforms like Twitter or Stripe ensure stability and fair usage under immense traffic? The answer is rate limiting. In system design interviews, discussing rate limiting isn't just a bonus. It's essential for designing robust, secure, and resilient systems. Today, we are diving into what rate limiting is, why it is crucial, and the algorithm you need to know. Okay? So, what is a rate limiting? Let's just take our pen. We have here a client and a server. Okay. At its core, rate limiting is a control mechanism that sets a limit on the rate at which an API or service can be accessed within a given time window. Think of it like a bouncer at a popular club, for example, or a speed limit sign on a road. Its primary purpose to protect resources, basically to prevent a single client, whether it's a malicious or a simply buggy, from overwhelming our servers. Also, it ensures fair usage, a guarantee that all legitimate users get a fair share of your system's resources. It also prevents abuse because it mitigates common attack vectors like denial of service, brute force login attempts, or aggressive data. So when the client sends a request, let's say that our client only allows 3 requests per second. So we have here our rate limiting. When our client sends 4 requests per second, only 3 of them will pass to the client, and this one will be dropped, maybe saved for later used. But like we only process the 3 requests per second. This is what is rate limiting on high level. Okay. Why rate limiting matters in system design? It matters due to so many reasons. We talk about 5 in this video. First one, it's protecting against abuse. Protecting against abuse. It's your first line of defense against various types of attacks. Without a simple script could bring your service down. Okay, without it, one service script could bring down our entire service. Number 2, resource preservation. It ensures your precious compute, memory, database connections, and network bandwidth are not monopolized by a few requests, protecting them for all users. Number 3, fairness. It's about ensure a constant experience for all users by preventing any one user from monopolizing the entire resources. Number 4, cost control. Like if you are paying for API calls to third-party services or for egress bandwidth. Rate limiting will directly helps control those operation costs. 5, interview differentiator. I would say it's bringing up a rate limiting shows a pragmatic understanding of building real-world production-ready system that can withstand real-world loads and threats. Okay, next we want to talk about key rate limiting algorithms. I will not go in details in any one of them. I will just, because I believe that each one of them needs its own video. I will create videos for each one of them soon. I guess I'll create a video to how to design a rate limiting system, and I will talk about each algorithm in details. So first we have lead bucket algorithm. This one, if you want to understand it, you can just imagine a bucket with a small constant leak at the bottom. Requests are like water drop filling the bucket. If the bucket overflows, like we have a new drop, which is the requests, the drops or the request here, they are discarded. Otherwise, the drops are processed at the constant leak rate. The pros of this one, it's a smooth out of process of request, ensuring a steady output rate to your back end. The cons of it, requests might be queued and delayed significantly during process. The bucket size can be tricky to tune as well. And number two, we have a token bucket algorithm. The concept of this one, think of a bucket that is filled with tokens at a specific rate, which like basically each incoming request consumes one token. If the bucket runs out of tokens, the request is dropped or queued until new tokens have arrived. The bucket has a minimum capacity allowing for bursts. The pros of it allows for bursts of requests up to the bucket's capacity, making it more flexible than the leaky bucket. The cons of it still requires careful tuning of bucket size and token fill rate. Number three, we have fixed window counter algorithm. The simplest approach, which is a counter, is maintained for each client. Maybe by IP address or API key within a fixed time window, like 100 requests per minute. Requests increment the counter. If the counter exceeds the limit, requests are blocked. The counter resets the exact start of each window when the time ends. The pros of it, it's very simple to implement and understand. The cons of it, there is something we call the edge case problem. Like a client could make nearly double the allowed requests around the window boundary. For example, if the limit is 100%, 100 requests per minute, a client could make 100 requests at for example, let's take my pen here at where is my pen? Yeah, here. I can make 100% at 0.5 and another 100% at 0.1. So there is only 2 seconds, but the client can make 200 requests on these 2 seconds. The solve to this problem, there is a sliding window log algorithm. This is much more accurate for each client. The system stores a timestamp for every request made. When a user request arrives, all timestamps older than the current window, which is 60 seconds ago, are removed from the log. If the number of remains timestamp exceeds the limit, the request is quite blocked. Well, not quite blocked, it's actually blocked. It's highly accurate, effectively solves the fixed window edge case problem. The cons of it, it's have high memory consumption for storing all-time stamps. And lastly, we have a sliding window counter. This is a popular compromise between fixed window, simplicity, and sliding windows logs accuracy. It combines a counter for the current window with a weighted counter from a previous window to estimate the rate. The pros of it, it's a good accuracy, avoids the fixed window edge cases. The cons of it's more complex to implement than fixed window counter. It's really more complex. Okay, so next we will talk about key consideration in rate limiting design. First thing we will talk about, which is a rate limiting key, like what defines a client that gets the limit: IP address, user ID, API key, session ID. You need to choose based on your base cases. Number two, response exceeding limit. Like when a client hits the limit, you should return and let me get the pin. Yeah. 4 to 9, which is too many requests, status code. It's also good practice to include a retry header telling the client when they can try again. Just also we need to talk about distributed limiting, like for scalable applications with multiple instances. Rate limits must be coordinated across all instances. This usually involves storing counts or tokens in a centralized fast data store like Redis. Okay. There is also generality, like should limits be global, per user, per endpoint, or per combination. Also, there is graceful degradation, like what happens if the rate limiter itself become a bottleneck or fail. Designing it to fail gracefully, perhaps allowing all requests through temporarily. We can do that. Also, we have blocking and throttling. Like, do you hard the block requests or do you queue them and process them more slowly, which is throttling, depends on your use cases. Okay, how to discuss it in systems and interviews. In systems and interviews, bring up rate limiting early when discussing an public-facing API or a system component that interacts with external services. Justify your choose algorithm based on the problem's requirements. Like, for example, I would start with a sliding window counter for accuracy and distributed support using Redis for centralized counts. This demonstrates a proactive approach to protecting your system's resources, ensuring stability and preventing abuse, all hallmarks of a strong system designer. So yeah, that's it for this video, and see you in the future, guys.